Our final lesson in Chapter 3 and of the semester is 3.5, Mathematical Modeling and Variation. We're going to look at 4 types of variation, which are different equations that model things in a different way. We'll take a look at how they compare to each other and how to write their equations from given application problems. The first type of variation we'll look at is the most common one, direct variation. Direct variation is the same as a linear function. And more specifically, the y-intercept would be at 0, 0. It says the statements below are equivalent. Y varies directly as x. Y is directly proportional to x. When you're reading an application problem, whatever's written before the words varies directly is on the left side. So that's always going to be the y value. And anything that's written after the words varies directly is on the right-hand side, and that's going to be like your like your x value. I meant to put right there. Here we go. And what you're going to want to do is model it like y equals kx, and k is just a number that we have to calculate. So it's almost like finding the slope for the equation of a line that has y-intercept of 0, 0. Now we call it like the slope, but the name for k is actually the constant of variation. The next type of variation is direct variation as an nth power. So it's very similar to the last kind of setup, but now your variable has an exponent on the right-hand side. So it says the statements below are equivalent. Y varies directly as an nth power of x. So n could be the squared power, and that just means you'd have x squared, the cubed power, and that means you'd have x cubed, the square root of x, and that just means you'd write square root x. So they all mean the same thing. Whatever's written on the left-hand side is the y value again for your word problem, and then whatever's written on the right-hand side is your x value. So whatever varies directly is on one side, whatever you're varying it to is on the other. Here's the format for your equation. Y equals k times x to whatever that nth power is, and k is still just that number that we're going to calculate. The next one is inverse variation. And inverse variation is going to be unique because it's a fraction with your variable in the denominator. It says y varies inversely with x, or y is inversely proportional. Now look at this fraction right here. You could either write it like y equals k times x, or you can move x to the other side and write xy equals k. Either way, that models inverse variation, and k is just going to be that number that we calculate. Our goal will be to just look at all the different types of application problems and find these key words that have been underlined in these definitions. Our final type of variation is called joint variation. And what makes this one unique from the other 3 is we have 3 variables. Notice it says z varies jointly as x and y. So now instead of just one variable on the right, we have 2 variables on the right. And then you'll write it in the format z equals k times x times y. And k is just going to be that number we calculate. As we look at the application problems on the back, the first step is to just determine the type of variation being modeled. What we do is we just write out the formula, and then we plug in the new variables from our word problem. We'll have given information to help us solve for k. And remember, k is just a number. We're going to write the variation model with that k in mind, and we'll keep x and y in our answer. So the example for this step would be something like y equals 2/3 x. Or we could maybe say y equals 7 x to the 3rd power. That's what your answers for step 3 will look like. And then in step 4, you may be asked to solve one final part based on your answer in step 3. That sometimes happens, but we don't always have to answer a final question in a word problem. So let's take a look at the problems on the back. You'll notice we have 4 problems, one to model each of the types of variation. The goal will be to read each problem and see if we can determine which variation model we're using, and then we'll go from there to write the formula. In Pennsylvania, the state income tax is directly proportional to the gross income. You work in Pennsylvania and your state income tax deduction is $46.05 for a gross monthly income of $1,500. Find a mathematical model that gives Pennsylvania state income tax in terms of gross income. If we look for our key words, I see at the very first sentence the phrase is directly proportional to. So that means the left side, the state income tax, is the output, and the right side, gross income, is the input. So this is directly proportional. If we write out that template first, y equals k times x, y equals income tax, and x is the gross income. It's the amount of money that you make before all your taxes are taken out. It says you work in Pennsylvania and your state income tax deduction is $46.05. So in step 2, we know what the tax is, and we know what the gross monthly income is. If we plug those two numbers into our formula, we get 46.05 equals k times 1,500. To get k by itself, you simply divide. And if you divide 46.05 by 1,500, we get k equals approximately 0.0307. And that would be an approximate 3% tax based on moving the decimal or two places in percentage form. So using this answer, we're going to go to step 3 and write our mathematical model. Remember in the definition for the steps, it says x and y are in your answer. So if y equals k times x, then our answer is going to simply be y equals 0.0307x. And that's the equation. That's all you do. We determine the type of variation. We identify our variables. In step 2, we use the given information to figure out what our constant is, like our slope. And then in step 3, you just plug it back in for the formula. And that's an example of direct variation. Here's the second word problem. The distance a ball rolls down an inclined plane is directly proportional to the square of the time it rolls. During the first second, a ball rolls 8 feet. Write an equation relating the distance traveled to the time. Then, how far will the ball have traveled during the first 3 seconds? If we think about finding our key phrase, now we have directly proportional to the square of the time. So that means this is going to be our direct variation to the nth power. Now the left side is going to be our output, and the right side is going to be our input, so x to the nth power. If we start out with that template, y equals k times x to the nth power, we know that the nth power is the squared power, so square of the time just means it's going to be x squared. Y stands for the distance the ball rolls, and x is the time it rolls. That's step 1, identifying the type of variation we're using and know what variables are in place. Step 2, it says, during the first second, so when time is just 1 second, that equals right there, the ball rolls 8 feet. So that's the distance. I'm sorry, here we go. Hang on, let's rewrite this. If time is 1 second, that's what x equals, not t. Sorry about that. 1 second. And then y is the distance. That's 8 feet. Okay, if we plug that into what we know, we've got 8 equals k times 1 squared. Well, 1 squared is just 1, so that means k equals 8. How easy was that? Plug that back in. Y equals 8 times x squared. And there's your variation model. Now, up above, we didn't have to do anything further than that. But now it says, how far will the ball have traveled during the first 3 seconds? So that's going to be our additional step 4. When x equals 3, I keep getting this confused. When x equals 3, we just plug that into our formula. Y equals 8 times 3 squared. Now think order of operations. 3 squared is 9. 9 times 8 is 72. That simply means the ball will have rolled 72 feet down that inclined plane. And that's an example of directly proportional to an nth power. Here's the next one. A company has found that the demand for one of its products varies inversely as the price of the product. When the price is $6.25, the demand is 400 units. Approximate the demand when the price drops to $5.75. So think about it. If you were going to go to a store and something was a certain price and it gets lower in price, you're more likely to buy it. So when the price changes, the demand will either go up or down depending on the direction of the price. So let's see how that works. It says that the product varies inversely as the price. So the demand for the product is our output, varies inversely as the price is our input. But this means we're going to have y equals k over x for inverse variation. Y means the demand of whatever the product is, and x means the price of that product. So just trying to figure out what our variables represent. In step 2, it says when the price is $6.25, that would be the x value, the demand for the product is 400 units. Plugging those two numbers into our formula, 400 equals k divided by 6.25. To get k by itself, we just multiply. If you have a calculator, 400 times 6.25 is 2,500. Substitute that into our formula to get the general rule, or no matter what the price is, we end up with y equals 2,500 divided by x. So there's your general formula. Now it says approximate the demand when the price drops to $5.75. Typically, it would make sense that the demand would go up. If the thing is cheaper than the original price, more people would likely buy it. So if we substitute in that new price, we would have y equals 2,500 divided by 5.75. And guess what? If you plug that into your calculator, the demand for the unit goes up to 435 units. And that's an example of inverse variation. And here we have it, everyone, the last example for the semester. The simple interest for an investment is jointly proportional to the time and the principal. After 1 quarter, the interest on the principal of $5,000 is $43.75. Write an equation relating interest, principal, and time. Then find the interest after 15 years. Now, in that very first sentence, we see the phrase is joint. Oh, whoa, come back. All right, hang on. We see is jointly proportional to. That would indicate that the value on the left, the simple interest, is our output, and that's the z value this time. Now, it's proportional to time and principal. So those would be defined as our x and y values, and you can put those in either order. That wouldn't matter. So as we set up our equation, remember the joint variation model is z equals k times x times y. So z is simple interest. I'm just going to write interest, keep it simple. Ha, get it? And then the x would be our time. Now here's the trick, everyone. Time is generally modeled in years. So we're going to have to adjust for that with that 3-month thing. And then our principal, that would be the original amount you invest. That's the $5,000. So that's the original investment. All right, so let's see what we know. It says after 1 quarter or 3 months, that's your time. So that's your x value. But 3 months is the same as 1/4 of a year, or 0.25 of a year. It says the interest on a principal of $5,000, that's the y value, our original investment. The interest is $43.75, so that's our z value. Lots to kind of decipher there, so just take your time working through those words. Plugging those variables into our joint variation model, we have z equals, so 43.75, equals K times X times Y, like so. To simplify, multiply 0.25 times 5,000, and we get 43.75 equals K just times 1250. To get K by itself, we'll divide. And this is kind of like what we did in that very first example. 43.75 divided by 1250 is approximately 0.035. And that would be how you would compare your interest from your principal over a given value of time. Now, we have to plug that into our model to get kind of the general formula. That's our step 3. Remember, Z, X, and Y won't be in it now, or the variables will be in it, just no numbers for those. So Z equals K, which is 0.035, times X times Y. There's your general formula. Then it says, find the interest after 15 years. So if for 15 years, that would be our X value. We know that Y is still going to be 5,000. It's our same original investment. Okay, so then Z is going to equal 0.035 times X times Y. So after 15 years, if you keep your money in this investment, you would earn interest of $2,625. And that's an example of joint variation. These are your notes for the final lesson of Chapter 3.